So welcome everybody to this workshop on Bayesian prediction and poststratification. I'm Roberto Cerina. I'm a sociology PhD student at Nuffield College, and I'm in my third year. And today I'm going to be talking to you about this technique, which is going to allow you to do a number of things. So why would you want to use this technique at all? You have two goals. One is to do small area estimation, which means if you have a sample that is representative at the national level, but you'd like to find out something about the state or the municipality or some other small area level, then this technique will allow you to extrapolate information from the national level and make reasonable inference at the area level. Something else that this technique does is it allows you to make inference at the national level for non-representative samples. And even at the area level, but as we will see, there is a few caveats there if you start trying to use it for the latter. And the title of the workshop is Bayesian Prediction and Poststratification. And the reason why that is because the Bayesian approach allows you to do simulations, posterior simulations, and this has big advantages in terms of computing confidence intervals of the area levels. Because you can simply simulate, if you're working with elections, for example, you can simulate multiple elections. If you're working with disease, you can simulate multiple rounds of the disease. And this gives you confidence intervals without actually having to go through the trouble of calculating posterior variances and so on. You can just use simulations. That's the advantage of it. And so there are three parts to the prediction and poststratification framework. So one is sampling, which we will talk about at the end, actually. The other one is the prediction part, and the other one is the stratification part. This workshop focuses mainly on the prediction and stratification parts. And in particular, prediction, we're going to be doing it, as I said, in a Bayesian way, which means that you guys are going to have to be... So how many of you are familiar with the Bayesian approach? How many of you have used the Bayesian approach in the past? 1, 2, 3... Okay, so 4. Not many of you. So I think a good idea is for us to go through a Bayesian primer first. Because how many of you are familiar with the concept of a Gibbs sampler? 1, 2, 3. Okay, so roughly like the same people. Okay, so this is very good actually, because I planned for 30 to 40 minutes of a primer to Bayesian modeling, and then we're going to get into the meat of the prediction and poststratification. And this primer to Bayesian modeling is actually going to be very useful to you to understand the basics of machine learning, because machine learning is ultimately, even though we don't have the computational power to do it in a purely Bayesian way at the moment, it is ultimately a Bayesian endeavor in its conceptualization. So you will see how this links to Charles' workshop later today, I think. And so let's start with the Bayesian modeling power. So first of all, this formula here is Bayes' theorem. You all know it. Bayes' theorem is a way to update your belief about the occurrence of an event after you observe some data. And so there are three parts to Bayes' theorem. P of theta. Theta is the probability. It can be an event, so it can be a parameter, any parameter. So for example, the probability of voting for a Republican in the population of the United States. And P of theta is our prior on that parameter. So it's a probability, and it's an expression of uncertainty. So we may have a prior on theta. We may say, okay, well, roughly between 45 and 55% of people are going to vote for a Republican candidate. So our prior is going to be some sort of uniform distribution between 45 and 55. That's a simple prior. And then we have the likelihood, which is this P of y given theta. So to understand that is a likelihood, which means it's the probability of occurrence of the data that you observe y, given the parameter that we have a prior for, theta. Okay? So, and as we will see in a second, theta generates y. This is where the Bayesian approach comes in. So like theta, the probability, the global, this like parameter that exists with uncertainty in broadly, generates data, and then as we observe data, we learn things about theta. So if we observe y, say y is the number of individuals who in a survey say they would vote for Trump, and if we observe y in a survey of n equals 1,000, we observe y equals 900, that suggests that our prior that was between 45 and 55% is wrong, or at least like there is a conflict between the data and the prior, and we should take that into account. Okay, and so this graph here, if I get there, illustrates the Bayesian paradigm. So there are two ways of looking at this graph. First, through the solid lines, and then through the dotted lines. So first, through the solid lines, parameter theta generates the distribution, the likelihood of y, and out of this distribution of y, you have observed values yi. So this is a random quantity, this is a random quantity, this is an observed quantity. Okay, so this is realized, this has happened, yi have happened. Yi would be, for example, the specific response in a survey that says, I vote Republican. Whereas y is the distribution of y's across the population. So if you were to ask the whole population without sampling, how many, like what the probability distribution would be for people to express that preference. And theta is the probability distribution of the hyperparameter, so the parameter that generates the y's. Does that kind of make sense to everybody, this kind of structure? So you have a generation of data based on parameters. Yes?
So, still a bit unclear the
difference
between theta and y?
Yeah.
So theta is something like the parameters that you defined to generate a distribution that has uncertainty of what y is.
Yeah.
And y is the actual distribution that was generated.
That's exactly correct. So theta is what we call a hyperparameter. If this were a normal distribution, it would be the mean, for example. And in the Bayesian paradigm, the mean has uncertainty, inherent uncertainty. So this is where the very difference between the Bayesian and the frequentist approach, which is probably what you've been taught through your statistics, comes in that the frequentist approach thinks that theta doesn't have any uncertainty. It's a parameter that exists and you have to measure it, period. Whereas in the Bayesian paradigm, we think that everything has inherent uncertainty. And therefore, as you observe data, you just change your distribution around theta. That's it. You never quite get to a precise theta. There's a paradox, which is that if you observe all the possible n's and in order to inform your parameter theta, then the frequentist and the Bayesian approach will converge. So if you observe every single value out there, you will be able to observe theta with zero uncertainty. And so you can imagine if this was a normal distribution, it would collapse on the mean. That's the idea. Okay. Any more questions on this? And so this y star is the predictive distribution. So before we observe any data, y and y star are going to be quite similar. Now here's the trick. When you then suppose that you haven't had access to the first part of this data generating process. This is, by the way, this conceptualization is called a DAG, directed acyclical graph, and it just serves to show the information flow within a data generating process. And so if you didn't observe this first part, but you only observed y, and you just hypothesized that a data generating process of this kind would have had to exist in order to create y, then you can use the information you gained by y to update your priors on theta and then generate a new predictive distributions, which means that if you were to try to predict the vote share of like a new person, n+1 person, then that prediction will be informed by the new data that you've observed. Okay, everybody clear on this? Perfect. Okay. So we've spoken about these priors and posteriors. So the way, let me go back to Bayes' theorem. The way in which Bayes' theorem is set up is that you have this prior, you have this likelihood, and then this updated probability distribution on the hyperparameter is called a posterior. And so the relationship between priors and likelihood determines the posterior, and there are some regularities in this relationship. So for example, there are sets of priors and likelihoods that are married, let's say, or as we say in Bayesian statistics, they're conjugates, which means that they have an analytical solution. So for example, I have an example here. A famous one is the beta binomial. Is anybody familiar with a beta distribution? At all? Yeah? Roughly, who's not familiar with beta distribution? Okay, a beta distribution is simply, very good. Please let me know when I'm not being clear. A beta distribution is simply a distribution defined between 0 and 1, and it, based on two parameters, alpha and beta, can take any sort of, it's very flexible. It can take almost any shape between 0 and 1, okay? So it's a perfect distribution to have a prior on probabilities. So for instance, the probability of voting for Donald Trump in a given election. And so theta can be, our prior can be, well, theta is distributed with two parameters, alpha and beta. And then we observe a poll, and this would be the likelihood. So the response of respondent Y, or respondent I, given conditional on the hyperparameter theta on which we have a prior, is distributed with a Bernoulli distribution. How many of you are familiar with a Bernoulli distribution? Okay, good. If that is the case, then you can simply, you don't have to do any math. All you have to do, so you don't have to do any integrations, you don't have to do anything. All you have to do is update your parameters, as we show here. I don't have a highlighter, but that's okay. And so you just update alpha and beta by summing the number of Trump voters to the alphas and subtracting the number of Trump voters to the betas. And that will give you your new posterior, so your new belief over theta. Does that make sense? Very good. Okay.
Can you talk slower?
So, sorry. I'll talk slower. Sorry. Very good. Okay.
So wait.
Yes.
Come
Yeah.
back real quick.
Yeah.
So
Yeah.
This beta part is the equivalent of when you take the actual observation, which is yi
Yep.
in this case, and
Yep.
you sort of integrate it with your prior, right?
That's correct. Yes.
That's the exact step when it happens.
Exactly. Exactly. So, in reality, in order to compute this, you would need to multiply the probability distributions of your priors and your likelihood. And that could be quite hefty. And you also have to divide it by the marginal probability of y. So that requires usually a lot of integration and a lot of multiplication, and that's quite a problem. The cool thing about conjugate priors is that somebody's already done that work for you, and they know that all you need to do is add to the alphas the y and subtract the y's to the beta. Yes, Chris?
Could you just give maybe an empirical example of updating of your priors? Like how do you observe distribution?
So, for instance, in a poll, right? So, if I had the probability, if my hyperparameter is the probability, the general probability in a population of voting for Donald Trump, then I do a representative poll of the US population, and I observe 30 people, in 100 people that is my N, I observe 30 people that say they vote for Donald Trump and 70 that do not. And then I would just go ahead and change the values for my distribution of theta to account for this. So, for instance, in the beta binomial or beta Bernoulli example, all I would do is subtract from the original value of alpha that I had in mind. I would subtract the number of Trump respondents, and to original value of beta, I would add, sorry, the opposite. I would add and subtract. Yes. Say it again. Sorry. Of course. So, as you can see, so probability distributions have inherent uncertainty, and the uncertainty around your observed value is going to depend on the sample size of your poll. So if you have a poll that has a very, very, very high sample size and it estimates the true theta quite precisely, then your posterior is going to be quite precise. Although, remember that what Bayes' theorem is actually an averaging via variances. So you have this likelihood and this prior. And what happens is, if your prior is really, 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 really precise, it's not going to move much when you observe new data. But if your prior is quite loose and your data is very precise, your prior will quickly shift towards your data. So it's, in fact, in situations where the prior is quite loose, we call that a non-informative prior, because it's not going to affect the estimation of theta. So it's almost going to be exactly the same as a maximum likelihood estimation. Does that make sense? Yeah. Okay, perfect. Yes?
So yi in your example is 0 and 1, yeah?
Yes, that's correct, yes.
So does it have to be 0 or 1 for the beta prior, or will it work with any, would it work for a continuous value of yi as well?
So for beta, beta is a prior on theta. So the distribution of yi, which is the 0, 1, is going to be a Bernoulli. And so if you wanted to observe, say, a continuous value for y, that would be, say, a normal distribution, there isn't a conjugate between a beta and a normal. But there is a conjugate between a normal and a normal. So if you had, for example, height or weight, then those are normally distributed, and your prior would be formulated not in terms of alpha and beta in a beta distribution, but in terms of mu and sigma in a normal distribution. And then you would then update that way. Does that make sense?
Okay, so you pick the 100 priors
Yes.
based on whether your data is discrete or continuous.
You got that. Yes, that's right. Any more questions? Okay, great. And so, having familiarized yourself with this, well, you might say, okay, but I heard that these Bayesian people, they're always doing stuff with computations. Why, if there is always analytical solutions which we can sum by hand, do people bother doing computations? And the answer is, well, in situations where your prior and your likelihood do not have conjugate form, like, for example, famous examples of this are a logistic distribution or mixture models. These don't have any conjugate form, so you can't find a nice combination of prior and posterior to give you an analytical solution. Then we rely on what is called Monte Carlo Markov chain methods. And the basic principle is that of a Markov chain. So a Markov chain is just, in fact, I'm not even sure you need to know what a Markov chain is, because I'm just going to give you an example of it. So we're going to look at the Gibbs sampler. So the Gibbs sampler is an algorithm that allows you to find your posterior in instances where there is no analytical solution between your prior and posterior. And the way it does this is as follows. So imagine you have a normal distribution. So you have two hyperparameters, mu and theta, the mean and the variance, okay? The variance in Bayesian statistics is usually coded as the precision, which is 1 over tau, so 1 over the variance. And the way the Gibbs sampler works is as follows. First, you set some arbitrary initial values for mu and theta. You might say, OK, I'm going to start with theta equals 1, sorry, mu and tau. I'm going to start with tau equals 1 and mu equals 0. And then you say, OK, let's sample. So imagine these are now distributions, right? Remember, so like you have this normal distribution, mu has a distribution, tau has a distribution, and you say, let's sample from the distribution of mu a new number based on the initial value that I put on theta. And then let's do the same on theta with the new value that I just sampled from mu. And then I iterate, so I continue doing this process until I reach some sort of convergence. So a typical example of this, I have this sort of whiteboard here. Maybe I can show you. This is very experimental, so bear with me. Should have been called the experimental social science. OK. Can you all see? Yeah? OK. So say I have tau, which is just the precision, or 1 over the variance on the x-axis, and mu, which is the mean parameter of a normal distribution. I would initialize mu and theta to be, say, here. Some low value for mu and some high value for tau, okay? Then I would sample a value of mu from this initial value of theta, and then I would do the same for a value of tau with respect to a value of mu. And then this would move me somewhere here. And then I would continue doing this. And if the properties of a Markov chain are reached, then eventually I'm going to get here, where this is the mean of the joint distribution, and this is the variance around it. So this is the uncertainty around it. So the idea is that if the properties of a Markov chain are respected, it doesn't matter that you don't have an analytical solution between your prior and your posterior. What you can do is simply iterate by sampling, iterative sampling. This is called conditional iterative sampling. So you sample from the conditional distribution of mu with the new values of sigma, and then you resample the new values of sigma from the conditional distribution of mu. And so eventually, this converges, and we have what I showed you here. So this is like the joint uncertainty around the two parameters, and the center would be the point estimates for the two parameters. Does that kind of make sense? Yeah? OK. Yes? Go on.
In simpler terms, this is like exploring the distribution of these two values, right? So
yes.
You're aiming to get to a distribution, right? And this will converge when you've visited all sort of like the bulk of the distribution.
Absolutely. Absolutely. Yes.
And that's why it takes so long when you have like very few data or whatever, because you're trying to explore a distribution which is maybe too wide or whatever.
That's exactly right. Yes. Yes. You might be familiar, if you've done some machine learning, so if you got to machine learning before doing the Bayesian stuff, you might be familiar with like stochastic search or like stochastic gradient descent. So it's a very similar algorithm in that sense. OK. So having learned what a Gibbs sampler is, you might be asking, well, when do we stop sampling? Because like you could just keep sampling all the time, but you don't know if you've reached convergence. Convergence is the key here. If you don't reach convergence, then you might have problems with stability. So it might mean that the next time you run the same model, if you don't have convergence, you'll get different estimates for your probability for your posteriors, and that cannot happen. Yes.
Sorry, I'm not really sure how to ask this question.
Okay.
In
In this thing.
are you sampling from the data, or are you sampling from the some hypothetical distributions, or so what does that have to do?
So.
How does that relate to my data?
Yeah. So your data comes in the conditional distribution of the mean. So in principle, you have a conditional the mean that you observe from your data, let's say, has this prior and then the observed data. When you sample from the conditional distribution of mu, you sample a new value of mu that has to be coherent with your data. That's the constraint. So there are two constraints here. Let me go back up, actually. When you sample the new value of mu, it has to be coherent with the current value of sigma and your data. So this is a coherence problem. Like every time you sample, it has to get more and more coherent with your data and your sigma. The reason why it doesn't converge sometimes is because your data is too sparse, and then there is also, as we were saying in front, there are all sorts of places where this algorithm could be. It could be over here, could be over there, could be over there. And so there's an infinite amount or a non-tractable amount of combinations of mu and sigma that are coherent with your data because your data is so sparse. Does that make sense? Okay. Yes?
So it's a method that you're starting by looking at those patterns, so you're not making any assumptions about the distribution of your data. You're just throwing the numbers in and saying, this method will give me that distribution.
That's correct. So the properties of the Markov chain that matter are that it is only dependent on its previous value. So it quickly forgets the initial values. That's a key property. And then eventually, that if you sample enough, it converges to a coherent joint distribution. Those are the two properties. So it's not that you're not making any assumptions. You're still making your prior assumption. So that comes in because your prior distribution, these conditionals will get you to a posterior, which is the average by variance of the prior and the likelihood. But what you're not doing is you're not letting your initial value for the search algorithm to affect the result. Does that make sense? Perfect. Okay. We're almost through the Bayesian prior. I promise. The Bayesian primer. Bayesian prior. And another way of looking at this blob that I drew on the board here is like this. So say this was just the mean of a normal distribution, and you were looking at its posterior, then there is a bunch of, so here we run two chains. So the way we spoke about a Markov chain, right? So like we run this algorithm twice, starting from two different points, and then we wait until X number of iterations where it's forgotten the initial values, which in this case takes around 200 iterations between the two chains. And then you can see that the two chains mix nicely, this is called mixing, which suggests that we are at this point here. We are at convergence. Because what does this mean? This means that every time I'm sampling from the previous value, I'm getting stable coefficients. If you imagine that this is mu, the variance here in each chain represents the actual variance of mu, the mean of the normal distribution. And so if both chains have agreed on the variance of mu, then you have reached convergence, really. Does that make sense? Yes.
What happens when chains are completely like random and independent?
Yeah, then it's a problem. Then it's a problem. It means that your algorithm hasn't converged. And as we will see, there is all sorts of tricks that you can use to try to get your algorithm to converge. But in principle, you cannot use your posterior values to make inference if the chains have not converged.
This could be potentially sort of like a disagreement between your data and your prior.
No. So if there is a disagreement between your data and your prior, your algorithm will still converge. It'll be like some sort of average in the middle, and it suggests that you should reformulate your prior really because, especially if you don't have much data, because your prior is affecting your data a lot, and maybe you don't want that to happen. It's not a non-informative prior. It's a very informative prior, and we try to stay away from those if you're trying to do predictive things, for example. Any more questions? Yeah.
So you want something that is not informative of the actual outcome.
So as a prior, you have two choices. If you know your stuff very, very well and your data is very, very small, you might want to pick something that's informative because that's going to go and augment your data. But the downside is that that might be biased, because if it's your belief about a given parameter, then you might have all sorts of bias in yourself. So for example, if I were to ask, I don't know, a non-minority person in America, what's the proportion of police arrests that involve minorities in the United States? My guess is they probably would underestimate that proportion. Whereas if I asked a minority person, they might overestimate it, and so somewhere in between would probably be more sensible. So, but I guess what I'm trying to say is, if you know that your prior is going to add value to your prediction, put it in. If you don't, choose a non-informative prior and allow your data to speak by itself. Does that make sense? Fantastic. Okay. And so the question comes, how do we choose when to stop? Well, we can look at these plots and say, and look at mixing, so as we just saw. But there's also a formula that we can use. And the formula is called the Gell-Mann-Rubin statistic. It's this R hat here. And all it is a measure of the within chain and between chain variance. So you need to, as I was explaining before, you need to have reached a sort of agreement between the two chains. And so if that is the case, the within chain variance has to be stable, and the between chain variance shouldn't be very large, because you want them to be converging on the same point. Does that make sense? So usually values of a Gell-Mann-Rubin statistics, that R hat, that tell you that your algorithm has converged, are anywhere below 1.1. Then you can sort of, this is a heuristic, by the way. It was developed by Andrew Gell-Mann and Don Rubin? Yeah. But you can pick, you should pick values that are below 1.1. There's also some discussion in the literature about 1.1 being too large and some conflicts with frequentist statistics once you get there. But 1.1 is a good value for you guys to know. And then the last problem you have is, as you sample from each one of these, you don't just have the problem of convergence, you also have the problem of autocorrelation. Because clearly, the value where you are today will affect the value where you are tomorrow every time you sample. And so in order to get rid of that, and the way you can estimate how much that autocorrelation is affecting your Gibbs sampler is through this thing called effective sample size. And all that does is it says, well, if you filter for the autocorrelation, how many truly new data are you getting every time you sample from your conditional distribution? And so if you think, like, if you do 100 runs of your Gibbs sampler, and you think that you have reached convergence, your effective sample size should be 100. But often what you find is that you do 1,000 rounds of your Gibbs sampler, and you think you've reached convergence, but then you look at the effective sample size and it's like 28, which means that your values are massively autocorrelated. And the technique you use to get rid of this autocorrelation is called thinning, which means instead of taking all the 1,000, you take every 5th or every 6th or every 10th and so on. And that should remove the autocorrelation because this is a Markov chain. Today's value is only dependent on yesterday's values, not on the days before. And so if you pick every 10th, they're going to be independent. Does that make sense? Brilliant. OK. So with this small Bayesian primer, I try to give you like 4 years of studying in like 20 minutes. But the learning objectives, you should be familiar with what Bayes' theorem is. You should know what a likelihood and a posterior is. You should understand the Bayesian inferential procedure, so that kind of data generation and then inference and updating that I showed you before. You should be able to use conjugate priors and know their limitations. You should be able to understand what a Gibbs sampler is and why you use that when you don't have analytical solution from conjugate priors. And then you should be able to check whether your Gibbs sampler is reliable or that it has converged and that it's not autocorrelated. OK, take a breather. This was Bayesian statistics. Very good. What's coming next is a lot more reasonable in my mind. So we're now going to look at this prediction and post-stratification part. So the way I'm going to teach you this is going to be through the example that I'm most familiar with, because that's what I use with my research, and that is voting. And in particular, trying to predict the percentage of people who votes for a given candidate from a non-representative sample. And so, for instance, we may be interested in knowing in 2020 if Joe Biden was the candidate for the Democratic Party, what would be the proportion of people in the United States who would vote for Donald Trump, either as a whole in the United States or at the state level, because that's important, because then you can calculate the Electoral College votes, and then you can find out who actually wins the election. Okay. The classic decomposition of that problem that I just explained to you is as follows. So what you want is you want to find out what is the probability distributions of people who vote for choice J and turn out, conditional on a set of characteristics. So these characteristics could be the gender of the person, they could be the race of the person, they could be the income of the person, the education, and so on. And whether they turn out, people either turn out on election day or they stay home. And so we are going to decompose this problem. This is a joint distribution between vote and turnout. And we're going to decompose this problem into two parts just by the definition of a joint distribution. And that's going to be the distribution of voting conditional on turning out and the distribution of turning out. And we're going to multiply these together. Okay. So that's fairly straightforward. So one way we have to estimate the distribution of turning out is the probability distribution of individuals who turn out is we do a non-representative sample, say through digital trace. We obtain characteristics on individuals through this digital trace. And then we try to use these characteristics to get, and we have some training data. So we know from a survey, let's say, whether these people turned out in 2016 or whether they say they will turn out in 2020. And what we do is just we fit a model to predict turnout propensity for each individual within our non-representative sample. And this model could be anything. It could be a linear regression. It could be a multi-level regression, as we're going to see. It could be a machine learning method like random forests or a convolutional neural network, and so on. What matters is that you pick the model that, given your limited data, because your data is non-representative, will allow you to make the best out-of-sample predictions. So this is a fairly common theme in machine learning, essentially. And what do we mean by out-of-sample predictions? Well, if we have a small sample, say like 1,500 individuals, but we are interested in, hundreds of thousands of categories of voters, then we will only learn about those categories of voters from the small sample that we have. So for example, if we have in our sample white male, the only race that we have in a sample is whites. But we have whites of like lower education, higher education, and middle education. And then we are asked to make a guess as to the how minorities in the United States are going to vote based on the whites that we observed. Then we're going to have to find out an algorithm that allows us to extrapolate from our limited non-representative sample into that unobserved category. Does that make sense? And so one way we have to do this is the multi-level regression. Why do we choose multi-level regression? We could, as I said, we could have chosen any other algorithm. And the answer is because it allows us to do this thing called shrinkage. How many of you are familiar with the term shrinkage? Yes, very good. So it does this thing called shrinkage, which is a form of regularization. And what shrinkage does is when you estimate a coefficient, a random effect coefficient, for instance, instead of the coefficient being exactly what you observe on your data for that particular category, so for example, if one of our variables is education, and we have 4 of them, let's say like low education, middle lower education, middle upper education, and upper education, then instead of your estimate for the lower education effect being exactly the mean of the low educated in your sample, it is going to be an average between the mean of the low educated in your sample and the global mean of the 4 categories. And that average is going to be a variance average. So it's going to be a compromise between the between variance of the 4 categories and the within variance of the single category that you have. So for instance, if you observe only one individual with low education, then your estimate for low education effect is going to be very close to the average of the 4 effects. Why? Because that estimate is very unprecise in your sample. Whereas if you estimate this, if you have a lot of observations for low education, but very few for the other 3, the effects of the other 3 are going to be shrunk towards the effect of low education. Did that kind of make sense? So the effect that this has in practice is that it allows you not to overfit your data. And what this means is that when you look at data that you haven't seen before, your data has not been as affected by noise, so your model has not been as affected by noise, and therefore you'll be able to make better predictions, better out-of-sample predictions. Very good. Okay. What you see on the board is a hierarchical specification for a simple multi-level turnout model. So we say this is a survey or a digital trace, and we have asked people, are you going to turn out in 2020? Then that distribution, TI, is the distribution of TI. This is our likelihood. Yeah.
Vote or not?
Yes. Turnout. Turnout, yes, no. 1, 0. And the distribution can be assumed to be a Bernoulli distribution. So a Bernoulli allows for a probability of a switch on and a switch off. And this has hyperparameter theta. And then we can just use a logistic regression to estimate the value of hyperparameter theta for each individual in our sample. Now, you see the subscript GI. That's because each individual in our sample, in our mind, is part of a group. And this is going to be very important when you're going to stratify, because you're going to find out that there are so many people of this particular group in a particular state or in your country. And we will see how we will do that calculation later. So the group is going to be defined by the specific combination of sex, age, race, education, household income, and state in this particular model. These are all the etas are all random effects. So they are estimated in the way that I have described previously. The beta are state-level predictors. So why would we put state-level predictors in an individual-level model? Well, that's because ultimately you're interested in a state-level effect, and the state-level predictor can be extremely predictive of individual-level choices, actually. So for instance, if one of the common variables that we put in the state-level predictor, if we're trying to predict turnout, is last year's turnout. And this ends up being quite helpful to do out-of-sample predictions for categories of voters that we have not observed in our sample. So these are categories of voters that we're interested in, but we didn't manage to collect because our sample was imperfect or too small, and so on and so forth. What you see here are priors. Yes, Chris?
Including those state-level predictors, does that also help potentially with bias caused by shrinkage of the state coefficient?
Yes.
If you've got a few in one state, but they are nonetheless important for what's happening in that state, if they're shrunk towards the national mean,
Yep.
that might actually...
Yeah, you're right. So the state-level predictor helps you curb some of the inaccuracy/inconsistency that your Bayes estimator of the random effect would bring in. Yes. So I think that's correct. Yes.
I have a question about,
Yep.
so obviously this is the standard framework, but then in a non-representative sample framework, you would also need to have the best state-level estimates from a similarly non-representative sample, right?
Well, you could put them in. If you had them, you would definitely put them in. Well, so in the case of voting, what we usually do is, so you're saying, for example, if we have a representative sample of voters in the Midwest, would we use the point estimate from that representative sample as part of our state-level predictors? Is that right? That's a good question. I guess there is a trade-off. Yeah, I think you would want to use a compromise between the latest available data and the preciseness of the data. The cool thing about having last election results is that they are precise. They are the value. Whereas a sample that is generated via telephone calling, for example, etc., has, as we saw yesterday with the total survey error, has many, many steps in which it could go wrong, and so you might end up introducing noise to your sample. But in principle, I would say for countries that haven't had elections, say, in 8 years or something, so I was thinking of working on a project in Afghanistan, and in that case, you would pop in survey data because that would be a lot more accurate, yeah.
And on a general level, this is a model to go towards some sort of ground truth from a non-representative sample, and the model will only work for similar non-representative samples, right?
This is a model to go to the best possible prediction we can have for a category.
Yeah.
And then that's not, so this is not doing any stratification work. The result of this model is not going to give you the result at the state level. We need to do extra work to do that.
Yeah, but I mean the data you use, like the input is basically norm-representative sample, right?
Yes, that's correct. Yes, absolutely.
So it would only
Yes.
work on that specific characteristic of norm-representative sample, presumably.
It would work on representative samples as well. In fact, what people do sometimes is they pop representative samples in here, representative samples at the national level, in order to find out how categories vote, and then stratify those categories at the state level in order to obtain area estimation. So the fact that the sample is representative shouldn't stop you from doing multi-level regression. Yeah.
The question I had is
Yeah, sorry.
in the Xbox example, right?
Yes, yes.
Let's say you're not asking people what they vote like, but whether they prefer Xbox over PlayStation.
Yep.
Right? You can still expand all the cells. You slice the data up into very small cells, but still there'll be a sample selection into those cells.
Yeah.
That people have an Xbox. Right?
For sure. Yes.
You ask them whether like PlayStation.
Yeah.
You ask the same question with a sample from PlayStation. There.
Yeah, yeah.
You couldn't use the same model, right?
Well, you couldn't use the same model. You'd want to adjust for that selection effect somehow. Yes, of course, yes.
So therefore, this one is tailored to the selection mechanism for this norm-representative sample, and therefore would not be, because it's probably like the Xbox model would very much upvote. Maybe there's one person who likes PlayStation.
Yeah.
Then you severely upvote this person, right? The model kind of
Yes. So like we saw yesterday.
Exactly.
Yes.
So let's say the norm-representative sample is of PlayStation users. Then you wouldn't want to upscale, but you want to downscale it, right?
So there is a couple of things there. So that kind of thing. So the guy that uses the PlayStation, which we would want to upvote him, I guess you say, right? Because that would make him more representative of the all. Well, then we should have PlayStation and Xbox as part of our stratification frame. Yes, that's what you were saying. Yeah, for sure.
And then we should also have some kind of estimate of the population that contains these variables, right?
That's exactly right.
Post-stratify if we don't have also these categories.
So that's exactly what Scott was saying yesterday, that one of the limitations of his work is that he has to rely on census that gets done in 2011. And as we're going to see in the next section, which is the stratification part, you do need accurate cell sizes, we call them, in the stratification frame. So you can't do this work if you don't have accurate cell sizes. Yes, that's correct.
So just very quick
Yep.
the question. So
Yep.
here on the line.
Yeah, take the microphone, sorry. Yeah, sorry for the live stream. I mean, I doubt that anybody in America is awake at this time. But.
So in the line of the coefficients here, where we have female, age, race, education, household income. So you're assigning, so this logit is the distribution that you're assigning to each of these coefficients. So the prior distribution for all is just the same, or you're assigning where are the
priors?
Yeah,
these are the priors.
Right.
So I try to use cheap notation to save space, but the idea is that each eta has its own variance parameter. Does that make sense?
Yeah, I wasn't looking at the definition of n, but the definition of n is down there.
Yep. Yeah,
okay, now
that's right.
Sorry.
So these are the priors on the etas, and they are shrinkage priors because each eta, even though it has like 5 or 10 categories within it, like say education has 4 categories if I remember correctly, they have a single variance parameter, which means that they'll be shrunk towards the mean of the 4 categories. Yes. And this way of parameterizing it, so I told you that in Bayesian statistics we use precision, which is 1 over the variance, as the specification for the normal distribution. And this way of parameterizing with a uniform distribution, a positive uniform distribution large enough on the logit scale, is a way of including a non-informative prior on the variance. Does that make sense to people? Yes? Because 5 on the logit scale is very, very large, so it allows for variance values between 0, essentially. Yeah, it's non-informative, I would say. Do you have I'm sure there exist better suggestions. Okay. Yes, sorry.
So you also have some information on the state level in this case.
Yep.
Do this estimate at the higher level have to be in line with the estimates you are looking for eventually? Like, is there a relation now that you look for state estimates because you're interested in calculating something at the state level? Or could have been also gender or something in this case?
So there have been studies that have put in gender level variables as well for the reason that Chris was mentioning, which is that introducing the gender level predictor would help curb some of the bias introduced by the shrinkage. But they've shown that they haven't done, like, so you could do that, absolutely. You could have a state level predictor, a gender level predictor, an age level predictor, and so on. But studies have shown that it wasn't, it doesn't increase predictive accuracy of these models. So it would just increase running time, and we don't want to do that, essentially.
So basically, you should make sure that these estimates at the higher level are at the level that you're interested in estimates.
That's correct, yeah. Any more questions? Okay, good. And so how can we fit this model where it's clear that this doesn't have, even though, well, it's clear that this doesn't have a conjugate prior, right? It's a very complex model, a lot of nonlinearity, etc. So the way we do it is through our Markov chain, and in particular we use two programs that are very famous for doing this. One is JAGS, which is what, because I come from like an epidemiology background or like a medical statistics background, JAGS is what I've been trained to use, which uses two algorithms, the Gibbs sampler and then another one called Metropolis Hastings, which you don't need to know for today. And another one is STAN, which is a more recent development, which comes out of Andrew Gelman's sort of political science background, but also it's better. STAN is better. If you can learn STAN, learn STAN. And the thing about STAN is that it's better because it uses this thing called Hamiltonian Monte Carlo, which is a way, which is somewhat similar to stochastic gradient descent in that it's a way to create shortcuts between the iterations. So it's a way to send you closer to the convergence point faster, essentially. But you don't need to worry too much about that. Just learn one of these two languages. If you're starting from scratch, I recommend you learn STAN. But JAGS is a very, very good program, and it's what we're going to see today. And actually, having spoken to some statisticians, they have a sense that JAGS, if you have many, many, many sources of information, JAGS is a better way to aggregate them than STAN. The other part of our turnout model, of our decomposition that we saw before, which, remember, we're still trying to find the joint distribution for voting and turning out, was the voting distribution. And in particular, so what I'm showing you here is a very simple example of a voting for Republican. So we just have a dichotomous outcome in a poll. Do you vote for the Democrat or do you vote for the Republican? Yes, no. And so this looks almost identical to what you saw before, but there are two differences. One is that, well, in fact, one main difference, and that is that this distribution of R is conditional on turnout. There are many ways to make this distribution conditional on turnout. One way is to just add turnout weights to each observation, and then to obtain the posterior conditional on the turnout weights. Another way, which is what I prefer and what I'm going to show you, what we did in the example that I'm going to show you next, is to actually estimate a different alpha for people who turn out and people who do not turn out. And the way you do that is by fitting a vote choice model. You simulate who turns out, and then every simulation you fit the turnout model, the vote choice model, to people who turn out in that particular simulation and people who don't turn out. And then you repeat this every time. And the cool thing about this is that A has a quite nice, like, intuitive way. It's like, oh, okay, every time I simulate, I get a bunch of people who turn out, and then I'm going to use them to make my estimation. And then also that incorporates a lot of uncertainty into our model, which is one of the Bayesian advantages, because you incorporate uncertainty. If you just put the weights in, you're not going to be able to incorporate the uncertainty about those weights. But by sampling people who turn out according to those weights and fitting a model in them, then your coefficients are going to incorporate the uncertainty derived from people who turn out and people who do not turn out. Does that kind of make sense? And so, yeah, and so this is it. You've seen this before. Okay, so here we go to our example. So the example is, thanks to the organizing committee, we got some money to do a survey online. We did a survey on Amazon Mechanical Turks. Are you all familiar with what Amazon Mechanical Turks is? Yes? Well, for those who don't, it's just a platform where you can put any what are called human intelligence tasks, And so, for instance, if you needed labels for a training set, like so you had like cat war, for example, so you can feed the Turks a lot of cat wars, like we saw yesterday, and the Turks would have to click on the cutest ones. Or you could do something else. You could ask them to transcribe an audio file, or you can do something else. You can ask them to fill in a survey, like we did. That's kind of cool about the Turks, is that the Mechanical Turks. If you're wondering about the name Mechanical Turks, is that this is a small aside. Back in, I think it was the 1800s or something, there used to be the circus. They used to carry around a chess player with a turban. And the chess player became known as the Mechanical Turk because it was a wooden figure that would play chess and beat a lot of people. And everybody was thinking, like, how the hell do they do it? Do they have robotics or something? And it's like, no, actually, there was a little person inside a box underneath the chessboard that played chess, which is quite funny. But that's kind of why we call them Mechanical Turks, because these are tasks that, in principle, we would like to have an AI do, but we don't have the AI to do this, so we give them to humans to do. Okay. So a few details about the survey. So the goal of these, we asked them a bunch of questions. Some of the questions, all of the questions involved their voting preferences in 2020, and some of the questions involved their voting preferences 2016. Why did we do 2016? Because we had a benchmark. We know the results from 2016. And I want to show you that through a very non-representative sample, which is the Amazon Mechanical Turks, because how many selection effects are there amongst people who select into being a Mechanical Turk, right? Like, you know, this is a completely non-representative sample. But as I will show you is that from this non-representative sample, we will replicate the 2016 election results almost to the point. Few details on the survey. We survey 1,500 workers on the 11th of June. Amazon MTurks takes 25% of the total fee, which is a bummer, because we asked for specific characteristics about the Mechanical Turks. So we asked that they were Turks that had on average an accuracy of 95%. We asked that they live in the United States. And we asked that they had been approved for at least 1,000 human intelligent tasks. So why did I do this? I wanted to screen out bots, because bots are a problem in all online platforms, and in particular on Mechanical Turks there have been papers showing that there is survey bots that just randomly click throughout. Another thing we did to screen out bots was we had a CAPTCHA in the survey, so a bot wouldn't have been able to fulfill the CAPTCHA task. Okay, do we need to do a break, by the way, at some point? What at? Okay, so we have time. Okay, great. And so it costed us around $1,000, and we obtained 1,500 responses. And yeah, that's it. So now we're going to get into... good. Okay. This is what I figured... You know, I'll take this opportunity. I think Sonke tomorrow is going to speak more about Mechanical Turks and teach you how to gather data from Mechanical Turks. But I wanted to give you sort of an overview of what a screenshot of a human intelligent tasks looks like. And so up here you have the percentage of human intelligent tasks in your batch. So we had 1,500 human intelligent tasks, i.e. we wanted our survey to be taken 1,500 times. And this collective was called a batch of 1,500 human intelligent tasks. And this was the description of the task. These are the qualifications that we asked for. So hit approval rate greater or equal to 95%, location in the United States, it was 500. We asked them that they had been approved for at least 500 intelligent tasks. And this was an example of what any given Mechanical Turk saw. So what it was simply where it says the link will appear here only if you accept the hit. The link to our survey would appear. They would click on it. They would conclude the survey. And then at the end of the survey, a unique code to each individual Turk would be shown. And then they had to input that code inside so that we could match the responses to the Turks. Does that make sense? Okay. Fantastic. Yep.
Sorry, this is just a clarification question. What's a hit approval rate of greater than or equal to 95?
So it means that I only wanted people whose human intelligence task approval rate, so the proportion of approved over non-approved, was 95% or above. So I wanted people who weren't bots, because bots would have a very low approval rate. Because people, sorry?
Who approves them?
You. I would go on to approve each requester. So the person who posts a survey is called a requester. Each requester has to approve each individual worker. That's the thing. Yeah.
And you could sort of look at the history of what they've done to sort of accept.
That's right.
Okay.
Does that make sense?
Yeah.
Brilliant. Okay. And so we conduct this survey. Oh, now I gotta. Unless you guys can read sideways. Okay. So we conduct this survey. And we ask for a bunch of categories. We ask for a bunch of information. So we ask for, as I said, vote choice and turnout behavior in 2016, but also some individual level characteristics. So like, oh no, sorry, these are not the individual level characteristics. These are this is the state. So this was an example of the question, by the way. So did you vote for the presidential election 2016? Potential answer, yes, no, can't remember, don't know, was not eligible. By the way, I got emails from people that were very happy that I was not eligible in because they had just been naturalized, and a lot of people only in their surveys only get to write, no, I didn't vote, and then they feel bad about it because like it's almost like they didn't do their duty. But I was happy that they were happy. Yeah. And we further ask, which candidate did you vote for president in 2016? With potential answers, Donald Trump, Hillary Clinton, third party, can't remember, don't know, did not vote. Notice that we introduced the third party issue here, whereas in the example of vote choice that I showed you before, there were only 2 options, which means now we're going to have to do some funky stuff with our model to allow for multiple options. Funky stuff, I mean, it's like, anyway. From multiple sources, including the census and so on, we also have some state-level characteristics that we're interested in. So for each state, we have the percentage Hispanic, percentage Black, percentage Asian, percentage non-college whites. That one's important because, well, it's become important in the narrative because of Trump. Percentage college grads in general, because as you know, Hillary Clinton was the first Democratic candidate to win, or I don't know about the first, but the first in a long time, to win college grads in the United States. Median income of the state, the percentage that the Republican won in 2016, the percentages that the Libertarian won in 2016, the percentage of the Greens, and the percentage of people who turned out in 2016. Now, before you ask, yes, we're predicting 2016 state-level results with 2016 covariates. Perhaps it's cheating, but the reason why I'm showing you this is because A, there is no direct circularity because we're using these models to inform an individual level model, and B, these are going to be the variables that you're going to be using to predict the 2020 result in your exercise. And so, yes, part of it was just I didn't think it was correct to go back to 2012 to get these statistics because given that we've asked the question today, this is going to be a better measure of the reliability of this model being able to correctly adjust for bias than a model that would have used 2012. So I think this is the closest thing we get to showing you that if it works in 2016, it's likely to work in 2020, kind of thing. Okay. This is the turnout model. It's almost identical to the one you've seen before. This is the vote choice model. So as I said, it's a little more funky because now we have to use this categorical distribution, which is just a multinomial distribution with n equals 1. So this time, instead of everybody answering, being able to say, I'm either a Democrat or a Republican, they can say, I'm a Democrat, a Republican, or a third party person, or NA. NA's in, this is actually a good point. Missing values in Bayesian statistics, if you have missing values in your outcome variable, that doesn't matter. You can just feed them in because the Bayesian model estimates the predictive distributions and then just imputes them afterwards. So it's an automatic imputation of the output values, which is pretty useful in a lot of scenarios. And so the categorical distribution just says, well, instead of having one probability distribution, either Democrat or Republican, you now have 3 probabilities. There's a probability for voting for Democrat, a probability for voting Republican, probability for voting other. And these have to sum up to 1, of course. And the other funky stuff that's happening is that, as you can see, the effects now all have this index nu, which is representing the vote choice. So you're going to estimate a state effect for each vote choice, for a state effect for the Democrats, a state effect for the Republicans, a state effect for the others. And the other funky stuff is that there is this identification constraint, which is, it's a sum to zero constraint. So the idea is that if you have party-specific effects and you have multiple parties, in a binomial model, there is already a sum to zero constraint, because the effect that is for one party is immediately against the other. Here we have to introduce that by hand. And so you can just have this sum to zero constraint. Sum to zero can also be repurposed as the mean. This alpha bar is just the mean of the choices. Yes. Maybe there's a typo here. But in any case, I think you get the idea. Okay. And so now there is this code. So
sorry, can you
yes.
Go back to the
Yes.
I really didn't get what you were saying with regards to the sum to zero. So
Yeah.
I think that we want all the effects to sum to zero.
We want the effects to, yes, we want the effects to sum to zero. That's right. So because if the gender effect, say, is positive for the Republicans, for the Democrats, and positive for the Greens, it cannot be that it's also positive for the Republicans. Does that make sense?
So we're looking at, and why is that not possible? I think that's what I don't understand.
Well, because
Interpretability thing.
yes,
Because it's difficult to think about as we fix them on a certain point. So they either end up left or right at this single point.
yeah,
But in a lot of the prediction is zero, right?
yeah,
Oh, okay. So one of them says at the baseline.
Yes.
We're comparing.
that's correct. Yes. Does that make sense? Yeah. Okay. And then you have this model. So you're going to get to work on this on your own later on. But I'm just going to go through the motions of showing you how you fit a JAGS model. So this is a model to replicate 2016 results. So the first thing you do is you create a list. This is in R, by the way. So you create a list with your model data. And we introduce the data. Notice that I introduced the vote choice as ones and zeros. So it's instead of being a single vector with 1, 2, 3, it's 3 columns with ones, ones, ones. The reason I do that is because there is fitting a categorical model on JAGS is quite expensive in computational time, and there's a well-known equivalency, which is the Poisson model. So you can approximate a categorical model with a Poisson model, and a Poisson model requires that you have 3 different choices on the output. Yes.
So I'm just wondering on a more conceptual level.
Yeah.
You're making a model based on 1,500 people which
Yep.
are self-selected.
Yep.
They're also temporarily selected, right? So if you would ask this at midnight or at 8 a.m. or 12 p.m., etc., you get a different selection rule into your 1,500,
Yep.
right?
Yep.
That part of the model, then you make a model to estimate things you know, right? So
Yep.
the actual election results.
Yep.
What is then the virtue of that model?
So the virtue of the model is that we're going to find out how accurate we can get to 2016, and then we're going to use the same infrastructure to predict 2020.
Yeah, but then if you predict it, you would need a similar selective 1,500, right? It's a model made for this 1,500.
No, it's sorry. To the same 1,500, I have asked who they voted for in 2016 and who they're going to vote for in 2020.
Okay.
Right.
Okay.
Yeah. But what do you mean? So you want to create different models for different selection rules?
No, I'm just saying it's only relevant in a predictive context. Then you cannot obtain any insights which will generally, right? You couldn't say that if the coefficient for gender is positive for Greens,
Yeah.
this is a general insight. It's an insight that holds within this 1,500 cells.
Yeah, for sure. Yes. But the idea is that through the shrinkage effects, you hope that by bringing you don't fit the data too closely, and so you can do better out of sample predictions.
Yeah, but it's not clear, right?
Well, if the selection effect is super strong and you have an account, so there is this assumption called ignorability, which is that I can ignore the remaining variables that I haven't introduced in the model as part of the residual. if that assumption is broken, as you suggested, but through some like very heavy selection effect, then I can't ignore it. So I would need to introduce it in the model and then in the stratification frame. So yeah.
It seems that the Xbox example works because within cells, being Republican or Democrat doesn't correlate whether you buy an Xbox or not, right?
Yeah, that's right. Yeah.
Therefore, the selection rule is basically 50-50.
Yeah. Or, well, they still have some selection because they end up overestimating, if I remember correctly, the Obama vote. But not by much. So they did well, but they did a little bit. It wasn't perfect, right?
So therefore, it would seem like you have to do a couple of tests, basically, whether the thing you're asking for, the selection rules really correlate.
Yeah. The assumption here is that the selection into the specific time and day in which we asked the survey is not heavy, and that the selection of being an M-Turker after you control for all these variables here there's none, essentially. That's obviously an assumption, that's obviously false, but it allows us to make, and as we will see, the results are pretty decent, so it suggests that it's not too far off, let's say.
We can agree that the mechanical Turk frame is only relevant in a prediction context and not as an inferential tool?
Oh, for sure. But I mean, this is true of the entire endeavor that I'm teaching you today. This is a predictive context. It's not an inferential tool. Yeah. Anybody else? No? Okay. So we continue. We specify these variables. And then we specify, so JAGS, the way it works is almost exactly as I showed you with those hierarchical models up there. So literally you say, predicted distribution, distributed with a Bernoulli distribution with parameter pi ti at the individual level. We add this to the, this is an interesting thing. So when people respond to their turnout question, there's a well-known phenomenon of over-reporting. And people have found that in the AENES, American Election Study, can't remember now, an American National Election Study, the over-reporting factor is roughly 13.5%. In Pew online surveys, the over-reporting factor has been found to be 17% and above. So what we do here, we do kind of a rough correction. So we estimate the model, and then we say whatever distribution you have for each individual, whatever distribution you have thus far estimated, subtract 17% to it. So if the distribution, this is simply shifting, if the distribution was, imagine like a normal with like a mean of like 70% probability, then now this is shifted 17 points down. And this actually ends up having a very positive effect on the estimates. You should remember, if you do vote choice and vote turnout stuff, you should remember to account for turnout over-reporting because it's really important. Obviously, this assumption is not perfect. In principle, we would have done another model from another information source that would have told us who is more likely to, out of these categories, to over-report and under-report, and then created a predictive value for each individual in the sample. But we didn't do that. We just assumed that people are across the board likely to over-report in the same way. So this is like a uniform over-reporting kind of model. Yeah?
Yeah, so in this context, what is over-reporting, like during the survey twice? Or?
No, so it's simply if I answer 1,000 people, and in reality only 500 of them voted, in my sample it's going to be 750. Just because people lie. Yes. Well, but they lie for all sorts of understandable motives, right? There is like social desirability. There is like they feel like perhaps a little ashamed that they didn't turn up to vote. All sorts of things. Yeah. Okay. And then we outline this turnout model. These are random effects at the state level, region effects, age effect, race effect, and so on. This is the state level predictor. Specify the priors that we specified above. Again, you'll get a chance to play with this code yourself, so you can start slow and then continue. So there's some cheeky stuff that is happening here, which I will explain in a minute. You might be wondering, what is this auxiliary parameter beta? And what happens is, in search algorithms, kind of like the Gibbs sampler, there's this weird phenomenon that if you over-parameterize and then monitor, so if say you're interested in parameter beta, and then you specify this weird big model for beta, which is like beta is actually equal to like alpha times x plus 0 and so on and so forth, then what you find is that by specifying these sub-models and not monitoring them, you're still just monitoring beta, your model converges faster. And the reason for this is a mathematical reason. There's been papers showing this. It's just that the search algorithm finds the correct convergence point faster, essentially. I haven't explained that at all. But like, I'll send you the paper and you can look at it. So here we like over-parameterize our state level predictor by multiplying it for a new variable auxiliary beta, which is distributed with a normal distribution. But we don't monitor it. We don't care about it. We care about this beta here, which is the multiplication of beta star and auxiliary variable beta. Okay, and then these are, as I stated before, these are all the, you see, a random effect with its random effect distribution and auxiliary parameter multiplying by the original random effect. Yeah.
Actually, did you see a difference in the convergence?
Yes, massive convergence.
When you take that off and when you
yeah. Yeah. So the model that I have fit for this, it ran for 7,000 iterations, and now it converges almost perfectly. There's a few parameters that could do tiny little bit better. But before I was using the auxiliary parameter, I needed like 15,000 iterations to do it. So actually, it's very useful to know these tricks. Yeah, very useful to know these tricks. Okay, vote choice model. So notice again, we're specifying essentially 3 different Poisson regressions that are bounded together by that sum to 0 constraint. This trick works so long as you introduce a individual level effect that has a non-informative distribution. This is a well-known, if you look at the PDF, there is a citation for this, and you can go and look at that paper. And it's quite neat because the Poisson distribution is very stable. The Poisson sampler, on JAGS and STAN is very stable. The categorical sampler is quite unstable, and so this stuff converges a lot faster. Okay, and then so these are the effects, as I said before. Notice that the way we specify the conditionality is by specifying, estimating a different parameter for whether people are predicted to turn out or not. And so essentially, we have 2 models here. One is a model for vote choice for people who do not turn out, and one is a model for vote choice for people who do turn out. It's kind of interesting. I don't bother monitoring the vote choice model for people who do not turn out because it wasn't part of the inference project that we were going to do here, or a predictive project. But it's kind of cool because if you want to find out which party would benefit more from getting people to turn out, a model of vote choice for people who are predicted not to turn out will tell you that, which is kind of neat. Okay, and this stuff below is almost exactly the same as before with the sum to 0 constraint that I described before.
This Poisson is on a 0-1 in practice.
Yes, so the Poisson distribution is just defined over positive values, but the values we fed it are 0s and 1s, and then we have to put that random effect, that individual level effect in order to have the random effect coefficients to be estimated in exactly the same number that it would be from the categorical distribution to the Poisson distribution.
And therefore this only works if the sample is relatively weighted, right? 0s and 1s, because otherwise you have some...
Yes, yeah, you're right. If some of your categories are very small, you run into problems, yes.
And then another question, because it's a prediction context, but do you leave out like a test set?
No, we didn't. That we didn't because what we are interested in ultimately, which is the prediction of the 2020 results. 2020 results haven't happened yet, and so we're happy with building the model with all the information that we have, and then putting out the best possible prediction that we can right now. The other reason is that 1,500 people for this kind of exercise is not much. So you don't have the luxury, really, to do 20/80 or 70/30, because even removing 30% of the individuals from this sample would mean that many categories would actually go empty, and that would massively decrease the predictive accuracy of your model. So yeah, you're right. In an ideal world, we would take 15,000 people, 5,000 we would leave out, fit the model, see how it did in 2016, do again 3 or 4 times to see whether the coefficients are stable, and then fit it for the whole thing. But
so you don't have a formal performance
We don't have an out-of-sample prediction metric, no. But we do have, yeah, so for the predictive model, you're right. We don't have a formal prediction mechanism, sorry, a formal like cross-validation happening. But the fact that you do have the hard validation of whether it works or not with respect to the 2016 results.
But then you use the same data to test results. Like you use the 2016 results to train.
Yes.
Yeah.
I think for sure you're right. So you're right that we could do better with prediction. So one thing that we could do is fit it with 2012 data. But even that is weird because the question that we asked them about their 2016 behavior, we asked them today. So they responded to that survey knowing what the average behavior was as well. So I mean, it's a weird question. In principle, the ideal case would have been we would have done a survey in 2016, would have done a survey today, and then we would have checked at each point an out-of-sample metric to test the exact model. I gotta say this is something that the literature doesn't do at all. So like most models, I think because you don't want to run into the problem of having empty cells, and also because data is so scarce. Again, like a sample of 10,000 is considered to be massive in this literature, whereas like in reality, for most samples. So Gelman et al., they don't do an out-of-sample metric, but they could have because they had 350,000 people. So they could have done that. Yeah, but that's a point well taken, I think.
There's some criticism in general about the multi-level context, especially Bayesian,
yep.
that by adding random effects
yep.
and being just in perspective,
yep.
You have so much degrees of freedom basically in fitting data that a sort of goodness of fit measure within data is quite weird to evaluate, right? So my question would be, have you evaluated the variance of the random effects? And does it account for like 80% of all variance?
We didn't evaluate so you're saying, did we do a level-specific R-squared?
Yeah.
We didn't do that, no.
Yeah. Oh, okay.
Because, yeah, sorry. You're right, sorry. So the question has been about predictive accuracy of this model outside of the sample in which the model has been trained on. And in particular, whether we did any cross-validation. So I don't know if I take that point about, so if you compare, I agree that any model that is tested on the training set, let's say, is going to have overfitting problems. But I don't take the point that multi-level regression is particularly worse. Multi-level regression is better at dealing with that than linear regression. It's worse at dealing with that than a random forest, for instance. Yeah. So because the shrinkage effect are a form of regularization. So they're meant to be there in order to help you filter out the noise.
So the thing I'm referring to basically is that multi-level effects are basically the same as a random error, like in a normal linear regression, right?
Yes.
In a way, right? It's like an additional error term.
Yeah.
If you would think of it in a classical sense.
Yeah.
And therefore, it will be quite strange to define performance of a model by the fixed effects estimates, the coefficients, plus the residuals, right? Because then, per definition, performance is 100%.
No, for sure. No, I get what you're saying. Yes. I get what you're saying. Yeah, we can discuss this more later. But in principle, your point is well taken. There is no cross-validation measure here. Yeah. Okay. And so yeah, we finish specifying the model and you'll get to play around with this model with the code. So don't worry if it looks daunting at the moment. We tell JAGs which parameters we want to monitor through this this thing here, and we then tell JAGs to run 4 chains for 7,000 iteration. Burn in the first 6,000. Burn in is like, you remember when I showed you that image of the chains and it converged after the first 300? Then burn in is the first 300. We just throw them away because we know that they're not independent and they're not convergent. Whereas the posterior, the last 1,000 are assumed to have converged, and so it's like as if every sample is as if we're taking a new value from the joint distribution. So the effective sample size is 1,000 essentially. Very good. So, yep. So two questions, two answers to that. One, 2 is good, but you can never be too sure. And 2 is you can run JAGs in parallel on R. And the way the parallelization works is that each chain is run in parallel. So instead of running a single chain with, oh yeah, sorry, we should have, this mic thing is a bit hard, sorry. The question was, why do we run 4 chains instead of 2 chains? And the answer is, A, because you can't be sure enough, and B, because of the way you can run chains in parallel on R, which means that you can run 4 chains with 250 useful. So if you think that your model is going to converge after 6,500 iterations, then you can either run the 2 chains for, if you want 1,000 values at the end, you can run the 2 chains for another 1,000 in each chain, or you can run 4 chains, 250 each. And because you can run it in parallel, running 4 chains, 250 each is faster. Does that make sense? Yes. Yes.
We're running 4 different chains.
Yeah. Yep.
We're running 4 different chains, but each chain sort of is like a Markov chain, so like a distribution.
Mm-hmm.
So where are we, from which of these chains are we drawing our values?
That's a good question. So what you do is you have these 4 chains. So the question was recorded. Sorry, I'm paranoid about this, Tina. So the 4 chains reach convergence after the 6,000th iteration, at which point from each chain we remove every 4th. So there's a thinning factor of 4 that leaves 250 observations for each chain. Then we stack them up as if they were all from a single chain. And then we just use this stack of 1,000 observations because, think about it, given that they have converged, or at least we assume that they have converged, they should be from the same distribution. So we can just stack them up, right? Yeah, that's the idea. Any more questions? Good. Okay. This model takes about 4 hours to converge. So yeah, it's a bit painful. It used to take a lot longer. I stressed out about this. But what you're going to play with in class is going to be something a lot simpler, I think. So we're going to pick 3 or 4 categories, and then we're going to let you fit a model only for vote choice and only for those 3 or 4 categories. So that should be quite fast, actually. I would expect it to take about 10 to 15 minutes or so. Gellman-Rubin statistics is shown here. So notice that some parameter, these guys here, are having a hard time to converge, but actually they're very close to 1.1, which means that if we run a few more iterations, they will probably converge. Yes?
Just a quick question on your opinion, because lately they've been using INLA.
Yeah. Great. Really, really good.
Okay, because the speed especially is...
It's super... So INLA is super... INLA, Integrated Nested Laplace Approximation, is a new Bayesian software which uses integrated nested Laplace approximation and assumes that instead of using the Gibbs sampler, it uses this technique that I just mentioned. But it has two disadvantages. It has an advantage, which is speed. Massive gains on speed. Disadvantages are that it's hard to bring in data from multiple sources in INLA, whereas here I can literally have 2 models linking to each other, which estimate data from 2 completely different data sources. I could have the British election study to inform my turnout model, which is actually what is done, and then I could have my survey to inform the vote choice model, which is actually what people do all the time. And you can stack those into the same model, which is super cool, and you can find nonlinear ways to join the 2 models. So that's really, really fun that you can do with JAG, super flexible, and with STAN as well. INLA, they're not quite there yet. So you can, if you're like a genius, you can figure out the way to introduce this new information via priors and penalize complexity priors and so on and so forth. But at the moment, it works more similar to GLMM. So it has a set of pretty standard models that you can run with it. And also it has the disadvantage that you will never be able to run mixture models on it because they defy the assumption of Gaussian latent field, which is the underlying assumption of integrated nested Laplace approximation. So, yeah, but it's a great. Yeah, very good. No, INLA is a great option. I use it for a lot of stuff, but not for this because I needed to bring in a lot of nonlinearities. Yeah, but actually, you could use it for this. We can talk about it later. Okay. So we have this model, it converged, and now it's time to, so we're gonna, the fact that it converged means that now we have this predictive machine, And we can use this predictive machines to make predictions about individual categories or categories of interest. How can we, which means that, we need to set up these categories of interest. We need to find out how many people from a specific category lie in the state of Texas for which we want to make the prediction for. And we take this number from the American Community Survey microdata, which is available online. And at the end of this talk, I will show you how to download it. Yes? No, sorry. I thought it was a question, sorry. We break down the population into the following characteristics. So we break it down into sex, 2 categories, age, 6 categories, race, 5 categories, education, 4 categories, household income, 3 categories, and state, 51 categories. So this amounts to a total of 36,700 cells, of which only 29,000 we actually find that are populated in the microdata. So that means that there are some cells that are so rare that a sample of, I think the microdata is about 3.5 million Americans, don't contain any of them. So these are very rare cells. This is kind of a neat plot, which is actually something that from my own research. In the bold line, you see, so this is an ordered, you take the cells, each cell, so each voter category, and you order them by the largest cell to the smallest cell, where the largest represents the largest proportion of the population and the smallest proportion. So some of these cells in the around the 30,000 index are going to have one person in them, literally. In fact, on the 30,000, there is one person out of 3 million that belongs to that particular voter category. Whereas some of the cells on top, these have like 300, 1,000 people, and so on and so forth. On the y-axis is the cell probability in the population. So if you were to sample at random from the population represented in the microdata, the largest category, after you cut it up in the way that we described, the largest category has about a 2 in 1,000 probability of being sampled. Okay, so these are very small categories. This is very, very defined target stratification. The dotted line represents the cumulative distribution. So that means that as you sum the size of these cells, you eventually get to 100% of the population. And the kind of neat thing about it is that even though we have 30,000 cells, the largest 5,000 make up about 80% of the population, which means that actually in terms of power, if you start thinking about power dynamics, how powerful should your sample be? Well, if your sample is powerful enough to capture the dynamic for the top 5,000, so long as there is not too much heterogeneity in vote choice in the other, in the remainder 20%, you're actually fine. So that's why some of these, even though if you did the math, in order for to have a sample that's powerful at the 90% level and have it work on an MRP approach or prediction and poststratification approach, you might need like 100,000 people. The reason why it works so well with smaller samples like 10,000 and 1,500 is because you only need to get right the top 5,000 cells. The rest you can kind of ignore. So long, obviously, like this is not true if you happen to live in a federation where each state is completely heterogeneous from the other. Then you cannot do this kind of work there. Yeah. Okay. So this is kind of this is kind of like a descriptive of how the stratification cells look like. Essentially, if you had to like order them and rank them, etc. And then this is actually what they look like in practice. So this is the cell ID on the left. These are the variables that represent a given category. So the top category is females of Hispanic origin between the age of 44 and 54, which are college graduates who earn between $0 and $49,000 and $50,000, who live in the state of Florida. And there's 241 such people in the ACS microdata sample. And if you look at the very bottom, you have these female, older race category college graduates who earn the same amount, and there's only one of them in the whole sample. So these counts, these cell counts, are what you're going to use to stratify your predictions from the multi-level regression model. Does that make sense? And now we're going to look at how exactly the stratification is going to happen. Before we do that, I want you to have a look at how unrepresentative the mTurk sample actually is. And so if you look at these, so on the x-axis, you have the population proportions, and on the y-axis you have the sample proportions. And you can see that our frame is quite so our sorry, I may have swapped the labels here. Hold on.
Yeah, they're not the same scale, right?
No, but that doesn't matter so much. Well, in any case, let's look at, they're different. That's what matters. The age is different. Presidential election is different. Yeah, I think, sorry guys, I think I swapped the labels. So, yeah, in reality, in our sample over-predicted Hillary Clinton. So our sample had more, yes, that's right. Do we have young people here? In any case, that doesn't matter too much. Sorry, I'm a bit fried. But the important thing is that the samples are different. That's the main takeaway here. If they were not different, they would be on the same y-axis. So the points would be exactly on the y-axis. Yes.
But then the issue remains. So just move the upside. So the issue remains so that they are either representative or not, based on stratification variables, right?
Yes.
And normally you would say, okay, we do a random sample after stratification, and therefore anything else that's left, which might affect whatever we're interested in, is randomly distributed.
Yes.
Which obviously this doesn't help or doesn't do anything with. So I'm just wondering why the stratification attempt is made when the sort of reason why it would stratify, which is basically within strata, it's a random sample.
Yep.
And therefore anything that we miss potentially.
Yeah.
Would be presumably randomly distributed, right?
Yeah.
So therefore, it seems a bit difficult to make the step in between, right? Because just go straight for the prediction if you're interested in predicting. Because the inference is obviously invalid, right? Because you know, like in the Xbox example,
yeah,
the inference is invalid.
Mm-hmm.
In this case,
well, but it works. So why? Okay, I think I get your point. I think it's a matter of how much error you're willing to tolerate. So like, if you think that your stratification result is going to be as good, is going to be of the same error as a random sample. So there's two ideas, right? You can either do a random sample and just take the point estimate of the random sample and that's it, or you can do a non-random sample, stratify, and take the point estimate of the stratification. Both are going to be wrong, but if you can tolerate the level of error of the stratified sample, you can do it a lot cheaper. And so for the same level of error, you need a lot less money to conduct the non-representative sample.
Because just one follow-up on that is,
yeah.
Let's say your non-representative sample comes from Trump rally supporters,
yeah.
right? So you go there.
Well, yeah.
You at some point find a white male between 20 and 40. You find a white female. You find immigrant, etc.
Yeah.
You can weight it whatever way you want.
You shouldn't sample on the dependent variable.
Exactly.
You should never sample on the dependent variable.
But you shouldn't sample anything which is associated with the dependent variable, right?
Well, yeah, in principle, yes. Yeah. But most, so the residual effects are quite small, and the reason why, so that you mean like the residual selection effects end up being quite small, because and you know this because these work, these stratification mechanisms work. But you're right. In principle, there is an issue with the residual selection effects. There is an issue. Yes. Yeah. Yeah.
It's not just an observation. If we go up
to
the
just an observation. If we go up to this table, right, you find that in the last group there's one people. Are we to tolerate that there is indeed no selection effect for that group?
But this is not. This is a sample of the population, not of the M-Turk.
Oh, right.
Yeah. So this is
if in the M-Turk
there was only one person.
Right.
It's a problem. But what happens there is that the shrinkage effect comes in. So if you have only one white person in your sample, but you have 1,500 non-white people, then the effect of the white person will be shrunk towards that of the others. So it's still a problem because maybe there is a strong white effect, but it's a lot reduced because the effect is shrunk because there's the white effect is estimated with very little precision because there's only one person.
Right. But if the selection effect is done on, let's say, like a swing state,
okay.
So So for example,
yeah. So if you only have one person from West Virginia, yeah, you're stuffed. Like in that case, yeah.
Right, because the selection procedure within that state is not random. Right?
That's right. So if you were trying to do a prediction, an area level prediction at the state level, and you were lacking individuals who make that state different from others, so individuals who are particular to the state and you don't have them in your sample, you're not going to make good predictions.
In this case, it doesn't matter, right? Because you're not going to make a prediction. So for District Columbia, within South Region, within female.
No, right, exactly. So, but
because you aggregate.
yes, exactly. So that's a key thing here. Like stratification means you are weighted averaging, right? And when you average forecasts, you always get, there is a rule that like if the forecasts are capturing different levels of noise, you're always going to get a better forecast in the end. And the weights improve that dramatically. So this idea that even if you're averaging over 10,000 categories for a given state, and 500 of those categories are kind of like dodgily predicted, but the important top 1,000 are properly predicted, you're actually going to get a pretty good estimate for that state, even though some of the categories were mispredicted. Does that make sense? Yes?
I guess I'm not understanding how the cell ID is applied. So
yeah.
They're kind of sorted, but then why do you start with 240 and you bounce to 1800?
No, so the cell ID is just, I took the stratification frame as it was, and I assigned it a cell ID. Oh, you mean in reference to the previous plot?
Okay, so the cell ID is not the same as the cell rank
sorry,
in the previous plot. Okay.
I should have made, you're absolutely right, I should have made this cell ID the same as the other one. You're right, sorry. Apologies. Yeah, Chris.
Thanks for this. It seems to be reliant, this method seems to be quite reliant on having pretty granular data like this for many millions of respondents. Right? So if we're talking about like, I'm interested in the Middle East and North Africa, this like just doesn't exist. You have censuses, but you can't get the individual level data. So is this method, are there other ways around this, or is this method just not appropriate for that kind of setting?
So I once briefly spoke to to Jasmine about doing this in Afghanistan. And she said that the last census in Afghanistan had been conducted the last like big survey, she said, had been conducted in 2007. So data completely outdated. God knows what has happened in the area-specific provinces since then. You have to do the extra work there to actually predict the cells counts and then apply the stratification to the predicted cell counts. Yeah, it's unlikely to work, I think, in those scenarios. Yeah. Yeah, no, for sure you could. For sure you could. You could try. So, but again, like, yeah. So the question, the follow-up question was, if you aggregate together a lot of surveys, could this potentially replace the lack of census data? The answer is yes, to the extent that the surveys are reliable. So, like, if you have so in India, when I worked on the Indian election, for example, we used the India Household Development Survey. Because the census data was limited in their crosstabs. So again, another big problem is that you have to use microdata usually because there's lots of crosstabs that you're interested, right? And often census crosstabs are very limited to like 2 or 3 interactions at most. So yeah, surveys can be a solution, but usually they have to be augmented via some modeling. Yeah, that's what I would say. Yeah. Yep.
So what do you do? So what do you do when, for example, let's say, like when you have a survey and the combination of these stratification variables leads to what you were saying, something like 2,000 cells being empty?
Yeah.
In terms of calculating the true proportion from the census to be used with the much smaller data. So what do you just exclude them with your, as you said in your plot?
So you have, if that situation arises, there's 2 things that can happen. One is those guys lie here, in which case, like, as long as those exact guys form the makeup of a specific state that you're interested in, usually this isn't the case, by the way. Usually these like smaller categories are kind of like spread out at random across states, so it doesn't really matter. But if so in the positive scenario, those guys that you don't have in your census samples are here. and you ignore them. It's fine to ignore them. In the negative scenario, they're here, and then you're absolutely screwed. There's no way to get around that. Yeah. Okay? And so yeah, sample very unrepresentative in vote choice. So I'm going by memory here because I don't know if I can trust these plots, but it overrepresents Hillary Clinton quite dramatically. It underrepresents Donald Trump for a fair bit, and it overrepresents third parties. So after we have estimated these quantities, P of G, so the joint distribution of turnout and vote, and then the conditional distribution of turnout, we can then estimate the area level proportion of people who will vote for a given party and turn out with this formula here. So QG is just the number of people in a specific cell G. PG is the joint distribution of voting and turning out in a specific cell. And then you sum over the categories up to S. Again, I should have paid a little more attention here, but you sum over the categories for the specific state, and then you recover the area level estimate for each party. And then you can do so not just at the party level. So this look here. This is conditional on the voter characteristics and the specific party, right? Whereas here we don't bother, and the specific state. Sorry. Whereas here we don't bother about the state because we're interested in aggregating at the national level, and so we can just sum over the groups by their weight and obtain the national level results for each voter category. Does that make sense for everybody? Yeah. This is just simple certification, weighted averages. That's all. And these are the results. So at the bottom, you see the raw Amazon MTurk estimates, and at the top, you see the predicted estimates by state. So there's a few things to notice. So first of all, correlations improve dramatically. Mean absolute error is shaved off by, on average, so 10 points from Trump, 5 points from Hillary, 5 points from the third parties. Turnout is shaved off by like 32 points. So we massively improve on the raw sample. There is clearly this phenomena called attenuation bias happening. So even though the correlation is really high, the variance in the predicted state level vote shares is very small, which means that what you're going to get is the correct order of the states, but very much shrunk towards the global mean. And that's an effect of the shrinkage and of the general trend to shrink effects towards the mean. What else should you notice? No, I think that's it. I think we can. So I think overall, I think we can be pretty happy with the results, given that at the state level, at least, we've shaved off a lot of error from the raw sample estimates. Now, the really cool stuff comes in when you look at the national level. And so if we look at these are the distributions of Republicans, Democrats, and third parties. The solid lines represent the MRP predictions. The small dotted lines, the thick dotted lines represent the 2016 actual result. And the small dots represent the raw prediction of the raw national level prediction of the Amazon MTurk thing. And if we look at the errors, so our error on Trump's vote share is less than a single percentage point at the national level, 0.5. Our error on Clinton is quite large. It's about 4 percentage points. So we overestimate Clinton by 4 percentage points. Our error on others is we underestimate them by about 4 percentage points. So what is happening there actually is we must have missed some selection effect that would have told us about the substitution effect between Clinton and third parties. So we'd have to go back and think about what that was all about. But that's what's happening here. No, this model is aggregating at the national level. That's all. So the question was, does this model use the state level result? The answer is no. It's just the aggregated, using state as another group and aggregating over as you would otherwise. So yeah, I mean, I'm pretty chuffed at that Trump vote point, like half a percentage point from the truth. The turnout, again, we overestimate turnout still, even though we had applied that uniform correction of 17 percentage points, but that's not news. People lie a lot about their turnout, and the survey data about turnout that we get from MTurks or otherwise, it's pretty crap. So in our 1,500 sample, about 280 people said they didn't turn out, which makes for very small proportions of people, and therefore probably we missed a lot of cases. A lot of groups were predicted to vote at higher levels than they actually do. And on the right is just an electoral college projection. So assuming there is a lot of stuff going on with the electoral college these days, so like a lot of states have signed to this pledge that they will actually give the electoral college votes to the person who wins the national level result. But I ignored that. I just assumed that each state is going to give the electoral college votes as they usually do. And so we would have assigned with this model a probability of Trump winning of about 23%, which is not great, but it's also not terrible considering that Hillary's vote share was initially overestimated. Trump's vote share was initially underestimated by 10 percentage points in the Amazon MTurk sample. Yes?
Do you know how that compares to some of the pre-election predictions that other people were doing?
Yes. Yes. The question was, do I know how this prediction, well, this is not a prediction, by the way, so it's kind of an unfair comparison, but how this estimate compares to some of the pre-election predictions? And the answer is, it's a lot better, but for all apart from 538. So 538, if I remember correctly, had a 0.27% Trump winning. Wong at the Princeton election consortium had a 0% Trump winning. Drew Linzer had a 1% Trump winning. So, I mean, you know, from survey data, given you can't really compare because this is post-hoc and theirs was pre, but given that the survey data has the same chance of being bad this time around as it did last time around, this should be encouraging because it suggests that if you do enough modeling, you can get to better results than your average predictor. Yeah. Yeah. Hold on. Mike. This. Sorry.
So just to go back one more time to the virtue of the model, because if you give me data of the actual results, I can make a model which probably predicts better, right?
No, but the results are not coming in at the state level, right? They're coming in at the individual level.
No, but if you give me all the same data, I could probably do pretty well, right? Like after the fact, because you asked them who they voted for, you use the state level results in the initial model.
Yeah.
So it kind of seems that it may be a bit of a workaround, right?
As I said to you before, you could have used instead of 2016, you could have used the Republican 2012 results.
Exactly. Which would be
more, so there is a number of conceptual reasons why I still think that's wrong, because again, we asked the survey today, not before the election. So this is not a prediction exercise, it's a replication exercise. But in principle, if you were to do a prediction exercise, as you will do at the workshop, you're going to be using the 2016 results for predicting Biden's or whoever else. But like, I agree that this is not a prediction effort. This is a re-estimation, replication effort, for sure.
Okay.
Yeah, but understand. Sorry, I just want to make this have this point come across. Understand that at this level, the state level results from last year are not playing any role. They play the role at the individual level model insofar as they were correlated with individual level responses. And actually, the chances that, so 2016 results would have probably been more correlated with individual level responses today about the 2016 behavior than 2012 responses, but it wouldn't have been that far off because state level behavior is actually pretty stable across time. And the correlations across state is pretty stable. So obviously we should have refit it using 2012 and seen what would have happened. But you shouldn't think that it would have been that far off because the results at the state level weren't that different from 2012 to 2016.
But I'm just saying, like, just as a hypothetical model, I would do a very simple stratification, namely say, I just take one person out of every state. I assign this person the state level results, like the 0.52 if it was 52%. Then I just explode it by the number of people living in each state, and then I get perfect results, right?
Yeah, but that's not what we're doing, right?
No, but I mean, you use it at the individual level.
Yeah.
And then you explode it, right? So in principle, this a bit.
You use individual in.
So you say this.
Well, so if you assign the state level result perfectly, I agree with you. But we're not assigning the state level result perfectly. We're assigning the correlation between the state level result and the individual level response, right?
Exactly. But then again, like from a virtue perspective.
Yeah.
Also from a replication perspective, you could probably do better, easier, right?
Yeah. Yes. Yes. Yes.
Okay.
Yes. No, of course you could do. Of course, the fact that there's 2016 results leads to a better estimate than 2012 results. 100%. I don't disagree.
You missed the certification part, so.
Yes. Yes. We're trying to show that stratification matters here. Yeah. Any other questions? Okay. And so we're almost there, guys. Yeah, there's a few considerations here. So one is that we would have done a lot better as well if we would have improved the sample. We would have increased sample size. Sample size is actually a very contentious issue at the moment in the MRP sort of literature. So one way to call this model, by the way, prediction and poststratification, is also MRP, multi-level regression and poststratification. And some people have suggested that so for estimating area level result from nationally representative surveys, MRP does a lot better with higher sample sizes. So error reduces dramatically if you go from 1,000 people in your sample to 10,000 people. For Amazon MTurk specifically, so for non-representative samples of this kind, some people, Goel et al., suggested that the name of the paper is surveys are non-representative surveys are cheap and reliable, or are they reliable, or something like that. But they suggest that actually there is a decreasing returns on these kind of samples because of other set. If you look at the total survey error, some other errors start overcrowding the sampling error. And so even if you had 10,000 people, you wouldn't do much better than you did here. But the point is, people don't know. And as part of your one potential SICSS project, if you'd like to study it, you could come talk to me. Sample size for non-representative surveys in poststratification context is very important, and people don't really know what the hell is going on. So that's one of the things. And yeah, that's it. So we can take 20 minute, 10, 15, 20 minute, you guys decide, break, and then we'll come to the workshop. Yes? Mike.
Okay, maybe dummy question after the end of all of this, but
no, don't worry.
So if I understand correctly, this whole exercise is to estimate a proportion.
That's correct.
So I'm just
not just a proportion, by the way. You can also do it with like height, weight. You can do it with BMI. You can do it with like any quantity that you want to be representative at the national level, but you only have non-representative estimates for it.
But it is to estimate a single, like, parameter.
Yeah.
Could you also use this same way of having a non-representative sample if you wanted to estimate relationships between variables? Maybe this is really a silly question, but you know what I mean? So if my aim is not to estimate the share of people who vote, but let's say I want to know if more educated people are more likely to have children outside of marriage, and then I do like such a quick and cheap non-representative survey, would I then be also able to infer these kind of relationships?
So I think that's an intriguing question. Can we apply a poststratification to coefficients, let's say? I need to think about that. Off the top of my head, I don't see, maybe you need to do some extra work, but I don't see why you shouldn't. I don't see why you couldn't. Maybe there's all sorts of reasons why you shouldn't, but yeah, I can think. Yeah, we can think about that.
But this is not something that is.
I haven't seen it in the literature yet, but also because I come at it from a perspective where at the moment it's being used for political science, so like predicting who votes, but also disease mapping, so like predicting like percentage of influenza cases in different states, etc. So at the moment it's mostly been proportions, as you say. Yeah.
Okay. Thanks. Yeah, things like that, yeah.
Second case, you shouldn't.
We can have a conversation about it afterwards if you want. Thank you.
Actually, I just want to.
Yeah.
I think it's a very good question. If you think about how the existing literature on trying to apply post-stratification has really been in forecasting or elections or things like you know, just trying to replicate survey questions. I mean, the general concept here is to go from a messy, dirty sample to a more reliable sample by essentially weighting, right? This is just a weighting exercise. So it could actually be an interesting question to try, maybe for a group project or something else, to think about maybe doing a survey with questions that you might be interested in, right? For example, taking a survey, a social demographic survey, doing it on a non-representative sample using a platform such as Mechanical Turk, right? And then finding a relationship that you would be interested in, essentially a relationship of some kind, a correlation that is well documented, and then seeing to what extent that works in a non-representative sample, and then compare it with something that you trust more, which is of course much more expensive. So taking a correlation from something like the British Household Panel Study or Understanding Society, doing it on a non-representative sample, and seeing if doing the reweighting allows you to get within the bounds of that. Because of course the big sell here is that you have 1,000-person survey, which is being done for $1,000, which is very cheap. And so it's potentially scalable if it works like that. But so I think it's an interesting question that could even be worth exploring as a project.
Just a quick question.
Yep.
I was recently looking a bit at the survey literature and these calibration and the racking algorithm, but I don't often see the link with Bayesian statistics. Can you tell me a bit more? It doesn't seem the survey literature, calibration literature, don't seem to be using the Bayesian. What's the link there? What's the
the MRP studies that let me preface, you don't need Bayesian to do this sort of stuff. You can do it with frequentists. There's absolutely no problem. Like, feel free to use instead of like running the model through JAGS, feel free to use GLMM and put in the model. That's number one. The advantage of Bayesian is that because you obtain simulations for your posterior, you don't need to rely on sampling assumptions in order to calculate a specific predictive distribution. You get the predictive distribution directly from the model. You don't need to do any extra work. And so, maybe it's being lazy, but like for me, having these simulations really helps conceptualize the problem. And also,
so just a question on that. How would be different? Because it's not completely that, but it's quite linked. We use, for instance, bootstrapping and non-parametric to derive calibration weights.
Yeah.
How that would be different from a Bayesian simulation?
So that's a method of deriving the weights.
Yeah, but also an uncertainty around the
weights. Uncertainty around the weights. Yeah, so
that is non-parametric.
So I'm not like overly familiar with that specific method, but from my general understanding of bootstrapping and that kind of thing, so you would obtain some measure of uncertainty.
Yeah.
I think the assumptions that lie behind the bootstrapping are different from the ones that come with the Bayesian models that I showed you here. I am very familiar, like the assumptions behind the Bayesian models are very simple. You can derive them from your 5 probability axioms. So you don't need to do any extra work to specify new assumptions beyond what is a probability. And so that to me is a very intuitive thing, but that doesn't mean you can't do it. So feel free to replicate these exercises by using the bootstrapping. The bottom line is they both get. The important thing for me is that we put it in our minds that you have to have uncertainty estimates. You have to have uncertainty estimates, and like a lot of the applications often don't, and it's a problem because then you can't do calculations like the probability of Trump winning, like we saw here. Like this 0.23 comes because out of 1,000 simulations, Trump wins 230 times. But if you didn't have uncertainty over the state level estimates, you couldn't do that calculation. So it's really important that you do have the uncertainty. But you're right. Like you can just do it with other ways. There are other ways of predicting weights and finding distributions around the weights. If that's all, maybe we'll take a break. Yeah. Thank you.